Yeah. This only works when what is cubic or derivative. It's kind of annoying. Yeah, it still doesn't hurt to calculate the derivatives with respect to, I'll loop over all I and j and then calculate the double partial derivative with respect to c and epsilon, ci and epsilon j. Let's not do otherwise. Let's say if what equals Newton. Just gonna copy from my video description, which I just wrote. Use just a random index. 1 and 2 or 0. What did I do? No, 0 and 1. So you could just replace this by it still looks like an E, doesn't it? Lazy font makers. Yeah, for example, yeah, if you're just very close to the root and say the actual next x would be 10 to the power minus 30 off, while you, I mean, relative say to some value like 1. Yeah, then it's say the relative error would be 10 to the power minus 30, but that's not possible. It doesn't fit in a double. So it's going to be noisy around, with an average around 10 to the power minus 16 or something. And therefore, obviously, that 10 to the power minus 16 then comes from the purely the epsilons, while this is neglectable, the exact value difference. So I define this G as the difference. Well, this difference is just that minus that, so that would be minus that. I don't like have a minus all the time everywhere. Let's do a minus sign here. Now the Gn is really just this. So the approximation for, yeah, I don't know, I used that. We don't have many subscripts, so I use an A, call it approximation, floating point, including floating point round-off errors. I dim hier. Yeah, so the G is equal to this minus that, which is equal to this. But then the approximation, so that means the one including the round-off errors, has a machine epsilon introduced because of the division. So if these things would be exact, then you calculate the division and shit, it doesn't fit, so we round off. And that round off then gives this, is represented by this epsilon here, which is, you couldn't, because we don't know what the value is, so we don't know what the round off error is. So we see this as a uniform probability distribution between plus or minus 2 to the power minus 16 or something like that. Yeah, the ascensions are so strong, I will never be able to write one that is better anyway. Yeah, it would be an interesting hobby thing, but and then the calculations of the f and the derivative, of course, also are approximates. Then see a here, right? So this is correct, and then we have. You can just continue with writing that out. So just fill in. There's an A too much here. I just fill in these values. Okay, multiply above and below with the derivative minus that. So you get here the derivative squared minus this epsilon 1 squared. Then we get this. Oh, I would really just leave it away, the square there. Let's do it in 2 steps. Okay, that was the end of the video description that I wrote before I started the stream. Excuse me. Okay. Yeah, so this can be ignored, of course. It's just a square of epsilons, and that means that we have just divide by the square of the derivative. And then if you multiply by this epsilon 10, then you have to ignore every other epsilon factor, so we ignore those two as well, which then means that you have f times fxn divided by fxn squared, so that would be f divided by fxn times epsilon. And then terms without any epsilon at all is the same thing, but then multiplied with this 1, so you might as well keep it like that. So that would be this part, and then we get the 1 times the terms here with just a single epsilon factor, which means that times that minus that times that. Already took care of this, and we're going to ignore that times that, because that's just 2 epsilons. So then you end up with this. I like spaces between my operators. Okay, now the funny thing is that these two contain different epsilons, right? They come from different calculations. This one has epsilon 0 till up till 4, 5. And this one has epsilon 6 up till epsilon 9. Myro, yeah, in the end maybe. So we take the partial derivative of one of the epsilon 6 till 9, then this is going to be completely 0. This is going to be 0. And the code is actually ignoring the exact calculation. I mean, we're doing that with precision of 256 bits, and that is being subtracted. So we are only looking at this part then, if you ignore this epsilon 10. So which is the case for every partial derivative except the partial derivative relative to epsilon 10, which is absolutely not interesting because it just appears here. So we take the partial derivative, say, relative to epsilon 6, then this is going to be 0. No, let's start with smaller ones. Yeah, no, let's smaller ones. So let's say we this is what I begin with, right? I is 0 here. So we do the partial derivative relative to epsilon 0. Then this is going to be 0. And then we are ending with, and this is 0, and we subtract that. So then we are going to end up with just this term divided by the derivative squared, which is then just this term which we saw before, divided by the derivative. So before we didn't do anything, and then with before I mean if watt is equal to, let's say, the cubic or the derivative. Let's choose the derivative. So if I do this, you see that these values are a little bit too much zeros here, or not? No. No, there's just a lot of zeros. But they are 0.2, which means 2 times the root. The root is 0.1. Or 0.03, which means 3 times the square of the root. And which is exactly what it's also printing it here, of course. So the square of the root is multiplied with 3 everywhere. That's those 4 3's. And the root to the power 1 is multiplied with 2. Which is, yeah, normal for the derivative. While if we change this to doing Newton, so now we actually do this calculation that well, the one that I just talked about. No, they're not nice numbers anymore at all. This doesn't look like a power of 0.1 to some small integer at all. But I just derived why that is the case, because oops. Where's my text? I just typed it in. Yeah. So for example, for the partial derivative of epsilon 0, we expect to get something, well, E0 divided by the derivative. So if you multiply by the derivative, we get again that same epsilon 0 that turned out to be very have neat numbers in it. So only 1 times some power of 0.1. And say, yeah, what about the C1? So you also do a partial derivative with respect to all the C's, of course. So we get, say, we did a partial derivative relative to C3. Then you end up with just this without C3. And then a partial derivative on top of that of E7. And then you end up with 3 times 0.1 squared, 0.03. Yep. So in this case, we just get 1 or 0.1 or 100th or 1000th. Of course, all the factors before the epsilons are 1. So let's do that and multiply it with the derivative. Already calculated the derivative above, so we can just print multiplying it with the derivative at the root. I'll show you where I get that here. The derivative at R0 is just, you know, the derivative of the cubic. And yeah, as expected, well, maybe not expected because it is a -1, but at least it's a nice number. And here again, that's +1 here. And then at I is 0, j is 7. You get something that is not nice. And this is also dubious. I mean, it's more or less 100th-ish, but very closely followed by noise. I don't know where that comes from. I would rather have at least a 6-digit precision. Like here, just a lot of nines. I think we are definitely on track, and I think I probably can also understand why for J7 it doesn't work. But let's go back to the formulas. So the first one that is now not very neat is still epsilon 0, but then J equals 7. And I lost again where I was editing stuff. I need a grep for something. G. That is. So. J is 7. Oh, J is the epsilon value. Oh, that is epsilon 7. Yeah, that's inside E1 then. Oh, it should be correct that we get something from E0, which is should look nice if the epsilons are in E0. So. And that is apparently the index of epsilon is J. So that J should be between 0 and 5. Let's begin with removing the assert, I think. So I can see all of them. So maybe we should just look at this one. That would be the epsilon. So, yeah, that's -1. Although this is -1 times 0.1. And this is -1 times 0.1 to the power 2. And this is -1 times 0 to the power 3. 0.1 to the power 3. And epsilon 0 does occur in every term. So this is completely correct, except for the minus sign. But I guess that minus sign is because we are not not discovering E0 here, but minus E0. Let's see if I can figure out if that is true. No. My formula is a plus here. Oh wait, I introduced the minus sign, but only in the comment, not in the code. So make it match this code without making changes relative to the cubic and the derivative calculations. I should not introduce this minus sign. So Gxn should be defined as this. Which just toggles the sign. I'm going to put it here on the minus. just invert these two. Good. So yeah, now it is plus minus E0. So we get minus E0, that's why it's all minuses now. Now let's see. That was epsilon 0. So epsilon 1 should also be very obvious. Control F, not Control G. Oh, that's interesting. That ain't a power of 0.1. Okay, let's look at this one first, because, well, it's 0. I want to know sure that it should be 0. Probably should be 0, but it is I is 0, J is 1. We get 0. I is 0, that is C0. And J is 1, epsilon 1. Yeah. So the C0 term does not have a factor of epsilon 1. So the partial derivative with respect to C0 and then epsilon 1 is 0. That's correct. But yeah, likewise, if you, well, of E0, right? So the rest should be cancelling and having a factor of the divide by the derivative in it. But I don't think that changed. Because if you take the partial derivative with respect to epsilon 0 and epsilon 1 for that matter, then E1 is still going to be 0. So this formula here is going to be equal to just minus epsilon 0 divided by the derivative. So this one cancels against the square. And we multiply it before we print it. We multiply it with that one, so we just get E0 still. As long as we take the partial derivative with respect to epsilons that are part of the E0, we get a term from the E0, and this is going to be 0 itself. So just 0, yeah. And then with a minus sign in front of it. So in the case of epsilon 1, I mean, so C1 epsilon 1, partial derivative relative to C1 gives me 0 everywhere except for this term, and then we take the partial derivative with respect to epsilon 1, and then I should get 0.1 with a minus sign. We should get minus 0.1. And we are not. What the heck? the heck? Okay, I haven't walked outside for a long time, like weeks, I think. It's not good. I think I'm going to do that right now. And while I think about this problem. Let's try without pen and paper, of course. I'm just going to walk outside. Let's see if I can figure out why this is not 1 in my head. That's definitely something to do. And something to think about then, right? I would say I'm never going to figure that out, but you never know. Yep.